Here we go. Okay, now we're recording. Okay, so this week is the last on intermolecular forces, the final topic. Next week will be a final exam review. Um, so, uh, so intermolecular forces. So as this name implies, we are talking about the forces that exist between individual molecules. Okay. And so what we've been talking about so far, water is shown over here in the PowerPoint. So, if I show the Lewis structure and I guess VSEPR, the shape of it, so we say that this is a bent shape of the molecule. Um, these bonds that we know them as covalent bonds. And so that means electron sharing, right? And it's really, to be even more explicit, covalent bonding, it's electron sharing between two nonmetals. Okay? And so these are really referred to as intramolecular bonds. Okay? So that is within one molecule, a single molecule. Okay, and so where these intramolecular forces are important when we talk about, for instance, last week we were talking about how much energy does it take to, break apart a molecule or to form certain bonds. Then we care about kind of these intramolecular forces. But really, the properties of the macroscopic material or substance depends on intermolecular forces. Okay, so that is when a whole bunch of these molecules come together, how much energy does it take to break apart those forces? So between this one and another one out here. Okay, and so if we kind of just look at water as the example, it's a liquid, as we know, at standard temperature and pressure. And so this STP that you might see in textbooks or in the media sometimes, that means 25 degrees Celsius. So what we consider kind of room temperature, and 1 atmosphere of pressure. Okay, so 1 atmosphere is 760 millimeters mercury or 760 torr. Okay, so all those are kind of equivalent pressure units. And so that, under normal conditions, it's a liquid. All other compounds, though, with similar masses, so, the molar mass of this is about it's 18 point something grams per mole. If you look at other compounds that have similar or even less masses, or I guess not too much more, but I guess oxygen would be, what is that, 32? This is 28. This is 44. So compounds with some smaller molar masses, they are all gases at that under these conditions, 25 and 1 atmosphere of pressure. And so having it liquid is kind of really rare for something that doesn't have much of a mass like this. And then also, we know that it has a very high boiling point, so it's 100 degrees Celsius. But if you look at structures with, that are kind of analogous, like H2S instead of H2O or H2SE, we find that they have much lower boiling points. And so it actually works out. I don't know if I have the data. I don't think I do in the PowerPoints. Oops. I don't. But if we look at kind of boiling points, and then we've got oxygen, sulfur, selenium, and tellurium. we find that, the H2S is there, selenium is there, tellurium is kind of there. It's not really linear. So you would expect H2O to be actually down here, much less, but it's actually up here for H2O. And so it has a much higher boiling point than any of the others in that same group. Okay, so these would be like H2S. Whoops. Okay, and so we'll see later in this class or on Wednesday why the general trend is that you increase boiling point as you increase the molar mass in general. Okay. Okay, and so oxygen is kind of this anomaly. Okay. And it all has to do with its intermolecular forces. And then the other one is when water freezes, it expands. And so most other liquids contract when they solidify. So that is, their volume goes from very large to very small. And so as a result, what we know in the wintertime is that, if we have ice, it actually floats, right? So that is the density of solid water is less than the density of liquid. Okay, and it actually turns out that this is the only substance where that's the case. Okay, if you look at anything else, the solid is always, so anything else, the density of the solid is always greater than the density of the liquid. Okay, and so again, all of these kind of macroscopic properties, physical properties of substances, it has to do with the unique shape of water. Okay, and so as I mentioned, we were talking about shapes of molecules. If water had this shape, that is linear, then none of this would be the case. It actually would not be anomalous, so it would also it would be a gas at standard ambient temperatures and pressures. So water would be a gas. And so imagine, if our bodies are, I don't know, like 80% water or more, imagine if we had steam, so instead of liquefied water, so our blood, in other words, would be a gas. Okay, so I don't think life would be possible under those conditions. Likewise, ice wouldn't sit on top of water, so ice would actually freeze all the way through, so aquatic life would die over the winter. So that would not be good. And then we wouldn't be able to dissolve any salts in water. And so, again, as far as our blood system, it has a whole bunch of different electrolytes and salts dissolved in it. That wouldn't be possible. It would kind of be like gasoline. So our blood would be more like gasoline than what it is now. And that's all because of just going from 180 degrees to 104.5. Okay, so life is possible because of, what is that, like 76 degrees difference in a bend in a molecule. Okay, so that's pretty amazing. Okay, so let's look at intermolecular forces, and it's all based on electronegativity differences. And so we've already talked about this concept. Again, just to remind you, so it's a measure of the attraction of an atom for electrons in a bond. And so it's that tug of war in a bond, let's say between these two atoms. That tug of war means that fluorine is really, really electronegative. So we can draw these little dipoles. Okay, so this is referred to as a bond dipole. Okay, and they point toward the more electronegative atom in a bond. Okay, so that's all it is. We can talk about, the magnitude or the length of these. So, sometimes, you have this if it's HF. If it's HCl, it's, chlorine is not as electronegative, right? So as far as like numbers, fluorine is the most electronegative, so has a value of 4. Chlorine only has 3, okay? So we might indicate that dipole like this. Okay, so it's still pointed toward the more electronegative atom, but it's not as big, right? So it's a shorter little arrow, which means that it's less electronegative, okay? And so another way we can illustrate that is with these little deltas. And so since fluorine is more electronegative, we can say that this end of the molecule is partially negative. So it's a partial negative charge, and that makes the other end partially positive. Okay? And so these are not, it's not the same as saying this. Okay, where that is negative, the fluorine end is a minus charge, that's positive. So we don't put them as individual charges because that implies that it's a ionic bond, right? If you say this, then that means that that's an ion, that's another ion, and there's really no sharing of electrons between them. Okay, so you have to be careful, of not putting individual charges, but all you're saying here is that this end is more negative than this end, just due to the difference in electronegativity. Okay? So any questions on sort of the symbolism in molecules? We're going to kind of expand on that today, but okay. All right, so we then, most of the time, will have polar covalent bonds. And what that means is that you have two atoms that differ. Okay, so if they differ in electronegativity, then that's known as a polar covalent bond. Okay, so basically if you have two different atoms, then that means they will be bonded by polar covalent bonds. Okay? The only examples of nonpolar covalent are if you have the same thing. Okay, AA or BB. Okay, or for actual examples, it's all of our diatomic, I guess homonuclear diatomic molecules. Okay, so remember those that had the same atom bonded to itself. So it's hydrogen, and then which ones? Nitrogen, oxygen, fluorine, chlorine, bromine, and iodines. 1, 2, 3, 4. Yeah, so 7 of them. Okay, so all these will be joined by nonpolar covalent bonds. Okay, that means that in this case, there's really no difference in electronegativity, one side of the molecule to the other. You can't say that, that end is minus, that end is positive, because it's the same atom, so they don't differ by electronegativity. Okay? And so it's really this case whether you have single bonds or, remember, nitrogen, if you do its Lewis structure, it's actually this. Okay, so even if there's triple bonds, this is still known as nonpolar covalent. I guess in this case they would be bonds, plural. Okay, and then likewise for oxygen too. Okay? All right, so nonpolar bonds mean same atoms bonded to each other. Polar covalent bonds mean two different, okay? And so you can calculate the difference. I'm not going to have you do this on the final, but you can look at the difference in electronegativity. And if I give you values from a table, you just subtract them. And so the difference in electronegativity here is 1.4, for instance. And so if you look back at these differences, you would say that an OH bond is, so an OH bond, that difference in electronegativity was 1.4. If you look at a, let's say a CH bond, that difference in electronegativity is going to be much less, right? So carbon is 2.5, hydrogen is 2.1, so that's only going to be 0.4. Okay, so we would say then that an OH bond is more polar than a CH bond. Okay, they are both polar covalent. Okay, so both are polar covalent, but you can talk about which one is stronger than the other. And that just comes from how different are these electronegativities in that bond. Okay, and so you generally will get the biggest difference if you go from one end of the periodic table to the other. And so, for instance, if you look at NaCl, okay, that's a pretty big difference. So you've got 3.0 for Cl, and then sodium is only 0.9, okay, from that table. Okay, so that is 2.1, okay, or very large value. And so in this case, you have a metal and a non-metal together. And so if you get a huge value in that's different as far as electronegativities, we say that it is so polar covalent, if you want, that it really loses being covalent. And so that's why you generally don't even talk about it being covalent anymore. It's really an ionic bond. Okay, and so in other words, we wouldn't write NaCl like that, where it's a line between them. We would just really write it like this. Okay, where there are 0 electrons between those two ions in this case. Okay, and so you see that really, where you start to go kind of above 1.5 or something like that, that difference in electronegativity, now it becomes ionic. Okay, and so there's kind of an extreme where, you've got nonpolar covalent, where it's the same atoms, where if we kind of look at that spectrum, okay, and then you are getting farther away, where let's say it's that one, where now it's polar covalent, and now it's ionic. Okay, and so it's kind of progression, if you will, where you've got electron sharing, but as the difference in electronegativity gets larger, then you're always moving toward more ionic character in the bond. Okay, so So I guess as you're moving kind of right to left in the periodic table, you're getting more and more like an ionic bond because the difference in electronegativity is getting larger. Okay? So does that make sense, hopefully, to everybody? All right. So, we talked so far then about really the bond polarity. Okay, so whether you can have nonpolar or polar covalent bonds. Now we're going to look at molecular polarity. Okay, and so these two do not have to be the same. Okay, so molecular polarity, as this slide says, it depends on the types of bonds as well as the shape of the molecule. Okay, and so this is where kind of our capstone experience, if you will, for this class, where we're now going to use all of what we've talked about these last few weeks of Lewis structures, finding out what the shape of the molecule is, now relating that to whether the molecule is polar or nonpolar. Okay? And so here's the way to do it. So to determine whether something is now a nonpolar molecule or polar molecule, you first have to draw its Lewis structure, always fun, predict shape, and that's that VSEPR. Okay, we looked at really just a few shapes. So we looked at, let's see, linear, bent, tetrahedral, Trigonal Planar, and Trigonal Pyramidal. I think those are the only ones that we really looked at in this class. Okay, so you predict its shape, and then you draw bond dipoles and see if they cancel one another. And I'm going to talk about what that means in just a second. Okay, so if all the bond dipoles cancel, then we have a nonpolar molecule. What's that? If they don't cancel, then we have a polar covalent, or a polar molecule, sorry. Okay, so what do we mean by bond dipoles canceling or not? Okay, so think about it as a tug of war, okay? And in this case, this is a linear molecule, so this is the Lewis structure for beryllium dichloride. And so if we were to draw those dipoles, okay, they would be pointing toward the more electronegative atoms. So we've got one pointing this way, one pointing that way, and it's the same atoms in these bonds, so it's the same length. Each of these arrows are the same length. And so does everybody see, if I'm going to pull in this direction and pull in that opposite direction with the same force, then I'm not going to move this center anywhere, right? So think about a tug of war where you've got the exact same force pulling on two opposite sides. You're not going to move this in one way or the other, right? So this means that the dipoles are canceled. Okay, so in this case, if you have a linear molecule with the same atoms on either side, now it is a nonpolar molecule. Okay, so we would say BCl2 is nonpolar. It's a nonpolar molecule. Okay, versus if you have water. Okay, so in this case, the arrows are going toward the more electronegative atom, and it's the same length again because they're both OHs. But now does everybody see that if you're kind of moving it in this direction, moving it in that direction, they don't cancel anymore, right? Because they're not in opposite directions. And so in this case, the bond dipoles don't cancel, they don't offset each other. And so water is polar. Okay, it's a polar molecule. Okay, and so for water to be nonpolar, it would have to have this shape. Okay, so if water were linear, now it would look like this, like that. Okay, and now does everybody see that is the opposite direction to that one, and so they cancel. And so linear water would be nonpolar. Okay, which means that water would dissolve in gasoline or oil. Okay, you know that oil and water don't mix, right? And so it actually, there's a rule, it's called like dissolves like. One of the simplest rules in chemistry. Okay, and what that means is if you have a certain polarity of your solvent, then, like water for instance, then it's only going to dissolve something that has a similar polarity. So in other words, if you have something that's polar, then it's going to dissolve something else that's polar. Okay? But we're going to talk about oil or, those hydrocarbons here a bit later today. And so we'll see that those are nonpolar. And so since water is polar, oil is nonpolar, they don't dissolve. Okay, they don't mix. Okay. All right. So what do you think about this? So let's go through our shapes. So far we looked at linear. So beryllium dichloride was an example of linear. And if you have this molecule, that is nonpolar. Actually, what about this one? What if you had this? Okay, or in other words, this molecule. I don't know if that's even a real molecule, but if you had that one, what do you think? Is it going to be polar or nonpolar? Any ideas? If you guess, you're 50% right, a chance of getting it right. I don't want you to guess, though. What do you think? Polar, nonpolar? So if this was nonpolar, okay, the arrows cancel. If I draw these dipoles for this molecule, I would say, okay, that one's got maybe an arrow that long because fluorine is pretty electronegative. Chlorine is not as electronegative, so maybe I'll draw it like that. Okay, so now what do you think? So do those arrows cancel each other now? So in other words, you've got somebody over here in this tug of war for electrons. You've got somebody over here with, really thick arms. He goes to the gym all the time, pulling. Versus on this side, you've got somebody who never stepped foot in the gym.
So would it be polar?
Yep, exactly. Yep. So these, so in this tug of war, it's going to be moved this way, right? So this arrow is bigger than that arrow, so they don't cancel. Therefore, it's polar. Yeah? Okay, so you only have nonpolar molecules if these arrows are directly in opposite directions, same magnitude. Okay, so in other words, all linear molecules will be nonpolar unless you have different atoms on either side, right? So as soon as we break that symmetry, now it becomes polar. Okay. All right.
Dr. Thalman, quick question.
Yes.
Could you try to use that analogy, like as we go through the examples, like with the tug of war and stuff? That seems to like make it make more sense a little bit.
Yeah, we'll do.
Thank you.
Yep. Okay. All right, so let's look at this one. Okay, so boron trichloride. What is its Lewis structure? So how do I draw that? So, just to remind you, I guess, of those steps, it's maybe been a while. So chlorine has 7 valence electrons, and you have 3 of them, so that's 21. And then we've got another 3 for the boron, so that's 24 valence electrons. Okay, so then we put that in the middle. We do these ones, so that's 6, 8, 9, 10, 11, 12, 19, 20. Whoops. 24. Okay, so it's just that. So remember, boron is one that is actually okay with less than an octet, so that's the Lewis structure. Okay, so now let me put up a periodic table so you can see. Right here. I'll just pick one here. Okay, so in BCl3, minimize that. There we go. How are we going to draw the arrows? In what direction are they going to point? So between boron and chlorine, which is more electronegative? Okay, so you're looking at which is closer to fluorine. Okay, so
chlorine.
Yeah, so chlorine is going to be more electronegative. So we'll draw these arrows like this. So they should be the same length, even if I'm not drawing them exactly the same. Okay, so that's what it looks like there. All these angles, remember, are, whoops, not 60, 120 degrees. So what do you think? If you have like something in the middle, and then you've got 3 people around you pulling, okay, so you've got this, and now you've got somebody out here, somebody there, and then somebody here. My beautiful drawings here. Okay, so what do you think is going to happen to the center, if anything, in this case? So you've got something, and now you've got 3 people around you from those directions pulling at equal strength. Is the center going to move anywhere? Yep, so I'm seeing one person is saying it's nonpolar. Yeah, so that means then, so the middle won't move. Okay, so in other words, all the dipoles cancel. Okay, so all these ones, those three, will cancel, and we have a nonpolar molecule. Okay, so for the trigonal planar, okay, so to kind of maybe get a tally going here, so shape and then polarity. Okay, and for shape, we are going to assume that they are symmetrical. Okay, so you have the same atoms on either side of those bonds. So we looked at linear. That was nonpolar. Bent, that was polar. And now this one is trigonal planar, and that is nonpolar. Okay. All right, so any questions about the trigonal planar example here? Okay, everything on the plane of your computer screen? Okay. All right, so now what about, so a trigonal pyramidal like ammonia, okay, not one that looks like this. And then actually do it like this. Okay, where this one is coming out at you. That's why I kind of drew it like shaded. This one is going back behind your computer screen. Okay. And this one is on your computer screen. Okay, so again, these angles are going to be a little less than 120. Okay, but not much, like maybe 118, 117, something like that. Okay, so now how are we going to draw those dipoles? So they're going to point toward where? They're going to point toward the more electronegative atom, which is nitrogen here. It's closer to fluorine. So we can draw them as this, that, and that. Okay. And so now think about it as a tripod. Okay, so like that kind of a thing. Okay, and now, if you're, in this case, they're all going toward the middle, but, maybe it's easier for you to think the other way around. So if you're pulling out, along all three legs of a tripod, are they going to cancel anymore, do you think? This one's maybe harder to visualize. Yeah, so these, in this case, they no longer cancel. Okay, so in other words, if you pull along each of these legs of a tripod, then you're going to move the tripod. The whole tripod is going to go down that way. Okay, so they don't cancel anymore. And so that means then the trigonal pyramidal is polar. Okay. And then I guess our only last one is tetrahedral. This one is tough to see. So let me draw it this way. Maybe this will be easier to see. I don't know. Okay, so if you think about something in the middle, so let's do methane as an example. And if I have carbon right in the middle, and then let's say our hydrogens are along those corners and these corners. So opposite corners. Okay, that would be a tetrahedron. So these angles are like about 109.5 degrees. Okay. So what do you think in this case? So if you're pulling, think about them kind of as pairs. So if you pull on these two and you pull on these two with the same kind of force, and as far as the dipoles, it's actually moving in, but maybe as far as like visualizing the tug of war, if you think about kind of pulling outward from that center, what do you think? Are they going to cancel or not cancel in this case? This one's pretty tough to see, I think. So in this case, they do not cancel. Okay, in other words, pulling on these two is going to offset these. Okay, so your center is not going to move any. And so since they don't cancel, whoops, then it is sorry, I totally screwed up. I think I said something and I wrote something totally different. Okay, so these two totally will offset these two. Okay, so they will cancel. Okay, the dipoles do cancel. Okay, so in other words, if you pull here and you pull there, then that center is not going to move. Okay, and so since they cancel, then it's going to be nonpolar. Okay, so tetrahedral then is going to be another example of nonpolar. Okay, so those are your 5 geometries that you looked at this semester, and assuming that they're symmetrical, that is whether they're going to be nonpolar or polar. Okay, and as soon as you break symmetry, so for instance, CCl4, that is a tetrahedral molecule. Okay, if you draw its Lewis structure, it's just this. Okay, so that would be tetrahedral, but as soon as you change that molecule to this, or anything else, okay, now you go from nonpolar to polar, okay, because they no longer cancel anymore. Okay, so any questions so far? Okay, so again, what's important here is that even if for nonpolar molecules, you still will have polar covalent bonds, right? It's just that they cancel. Okay, so let me go back to this example. So CH4, does everybody see that we had a nonpolar molecule, but each of these bonds is polar covalent, right? Because you've got 2 different atoms in that bond. Okay, so maybe I should say that polar covalent bonds will lead to either polar or nonpolar molecules. Oops, it just depends on the 3D arrangement. Okay, so what shape the molecule has really depends whether the whole molecule is polar or nonpolar. Okay. So everybody's cool so far? Hope I haven't blown your minds too much. Okay, so the last place I want to get this today is talking about now sort of who cares, right? So how do we move from this to knowing what type of intermolecular force we have? Okay, so let's talk about the intermolecular forces that we have. Okay, and so there are a few of these. So the first one we have is an ion dipole force. Okay, and so this is between either a positive or negative ion and a polar molecule. Okay, and so an example of that would be, let's say, sodium plus that is attracted to water. Okay, so this end of the molecule, oxygen is more electronegative, so it's going to have a delta negative charge. Water, the positive ends are that. Okay, and so this would be an example of an ion dipole force. Okay, so this dipole just means that, you know, it has a charge on one end of the molecule. Okay. Okay. And you could also have like a negative charge. So in that case, it would be attracted to the hydrogens in water. Okay. Opposites attract, right? So your kind of partial positive will be closer to the minus of the ion. Okay, so both of these would be examples of ion dipole forces. Okay. Now, the next one would be dipole-dipole forces. And this is between two or more polar molecules. Okay, and so think about, let's say, this one and this one. Okay, this is a, I'll just say dip-dip. Okay, so that's a dipole-dipole intermolecular force. Okay, so when you heat up HCl, okay, so let's say we have HCl liquid, we're going to heat it up, so that's the symbol for heat, and then we're going to boil it, really. What's happening is you are not breaking these bonds, okay, but instead you are breaking these ones. Okay, those are the weakest. That's why we draw them with dashed lines. Okay, so when you boil something, you are only breaking its intermolecular forces, not the intramolecular. That takes a lot more energy. You have to hit it with a laser or something with a lot more heat. Okay? All right, so that is between two or more polar molecules. Now, there's a subclass of dipole-dipole. Okay, so if you have very polar molecules, so in other words, if you have these, then it's still a dipole-dipole, but we indicate it as a very strong type. Okay, so a very strong type of dipole-dipole bonding actually has its own name. And so these are called hydrogen bonds. Okay, so they're really a subclass of dipole-dipole. And they only occur if you have huge differences in electronegativity. So you've got hydrogen with the most electronegative atoms. Okay, so fluorine, oxygen, nitrogen. Okay, anything else, like HCl, for instance, that's dipole-dipole. But if you have HF, that would be better termed hydrogen bond instead of dipole-dipole. Okay, and so if we look at water, that is an example where, if I just draw a few of these, and then maybe, you know, I can have hydrogens coming here. Whoops. Okay, and then maybe, I don't know, another oxygen here, etc. Okay, so all of these are called hydrogen bonds. Okay, and as the name implies, instead of force, up here, I called these dipole-dipole intermolecular forces. This is saying that they're hydrogen bonds, so the term bond means pretty strong. Okay, and so in other words, for you to break apart water molecules takes a lot of heat. And it takes a lot more heat than it would take to break apart these, for instance. Okay, so this is just a dipole-dipole. Okay, so let's say, I'm just going to pull a number out, but let's say that this takes, I don't know, 160 kilojoules per mole of energy to break, or it won't be nearly that much, yeah, whoops. Let's say, I don't know, 10 kilojoules per mole, let's say, to break apart those molecules. This one would be like 60 kilojoules per mole, okay, or 5 to 6 times that amount, okay? And so this starts to make sense then as far as why, if we look at two molecules that have the same structure, but you're just changing the group, so H2O versus H2S, okay? They have the exact same structure, okay? If we want to do the dots here for Lewis structures, so it's exactly the same. Angles, comparable. They're both bent. But the boiling point of this is 100 degrees Celsius, whereas this one is minus, I don't know. Hey, Google. And it's not working. Okay. Here, let me use my phone. Hey, Siri. There we go. What's the boiling point of hydrogen sulfide?
The boiling point of hydrogen sulfide is minus 77 degrees Fahrenheit.
Yeah, what is that in Celsius? Minus 77. So 25, okay. So I guess it's not as low as I thought. Okay, so 25 degrees Celsius, okay? So these are boiling points. And so that means, going from liquid to gas, okay? So we're breaking apart all of the intermolecular forces, okay? And so in this case, you are breaking apart dipole-dipole. In this case, you're breaking apart hydrogen bonds, okay? H bonds. And so this is a lot stronger. So as a result, you need a higher temperature to boil, okay? Or break apart all these intermolecular forces, okay? So does that make sense? So generally then, as the strength of the IMF, intermolecular force, goes up, the boiling point will go up, okay? All right. Okay, so that is the second type, I guess a subclass of two. And then really the only other one is the weakest. And so this is called London Dispersion Forces. Okay, and you can think of this as really an induced dipole force. Okay, remember like the second one we said was dipole-dipole? This is really an induced dipole effect. And what I mean by that is that this is between two or more nonpolar molecules. Okay, and so for instance, let's look at, well, I guess an easy one. Let's look at this one. Okay, so chlorine gas. Okay, so this one, it doesn't even have one part of the molecule that is positive or negative, right? Because it's the same atom on either side. But so it's not really apparent. How can this attract another one of these? Okay, so how does this even happen here? Okay, because you don't have these things that are kind of attracting, right? And so what happens is, if you think about this as this bond, if I take a kind of a blow up of that bond, okay, so here's the bond, and then I'm looking at electrons, right? So on average, those two electrons are right here. Okay, they're right in the middle between these chlorines. Okay, so that's on average. But if you take a snapshot of that bond, like on femtosecond time scale, really, really short time scale, you might see the electrons as, maybe one there and maybe one there, okay? Or maybe you'll see the electrons like this, okay, where two electrons are kind of nearer this side of the molecule, okay? And so the electrons are always moving around, okay? They're in certain orbitals between those atoms, and they aren't fixed in position. And so at any one time, you could have two electrons that are a little closer to this side of the molecule. And so that's what I mean by induced dipole, okay? That just because electrons are moving around, you could end up with a very slight charge on this side that'll then make that one a little positive. Okay, and when that happens, now you're going to attract another molecule where maybe this side has fewer electrons on that really short time scale. Okay, and so as you'd imagine, these are very weak forces. Okay, and so they can become stronger as you have larger atoms. Okay, and so London dispersion forces increase as the molar mass of the molecule increase. Okay, and so for instance, if you look at fluorine, chlorine, bromine, and iodine, we would find that as you go down the group, the boiling point is going up because the London dispersion forces are getting stronger and stronger. Okay, and the reason for that is because, if you have fluorine, maybe those two atoms are that size, versus iodine, they may look like this, huge atoms. Okay, and so if we have our nucleus here, and then valence electrons out here, okay, and then nucleus and electrons. Okay, does everybody see in this case for fluorines that the electrons are very tightly bound to the nucleus? Okay, just because they're really close, whereas here there's quite a difference between electrons and the nucleus. So that means that the next iodine molecule can approach and move these electrons a little easier. Okay, so electrons, I guess, kind of, if you think about it this way, as you get larger atoms, then the electrons are easier to move around, so then they are, the induced dipole becomes larger. Effect goes up. Okay, so it's kind of tougher to visualize London dispersion forces, but just remember, as you get bigger, then it's stronger effect. Okay, but kind of as the trend, as far as kind of in general, like the strength of these, we would say that ionic bonds are much stronger than covalent bonds. And then covalent bonds, so these are our intramolecular forces. Okay, then covalent bonds are stronger than hydrogen bonds, which is stronger than our dip-dip, okay, dipole-dipole, which is stronger than London dispersion. Okay, I guess we did ion dipole in there too, didn't we? Yeah, so probably in here. Yeah, so ion dipole kind of fits in there. So it's even stronger than hydrogen bonds in general. Although it depends kind of what ion you have, what molecule. But... Okay, so that's the kind of the strength of these. Okay, so increased strength, which means increased boiling points or freezing points. Okay. Okay, so a lot of material, I know, I covered today. On Wednesday, we will look at applications for this. Okay, so we're going to look at some varieties of, what type of molecules have hydrogen bonds, or these other dipole-dipole London dispersions, and then just look at, how does that affect their properties. Okay, so any questions? No question? There? No? Okay. All right, well, enjoy the rest of your day, and we will catch up on Wednesday, I guess, with our last lecture of new material. All right, take care. Yes, I mentioned a review last week, or next week. So, yeah, Wednesday will be the last lecture on new material, and then next week I'm just going to just do a review. Is there one on Blackboard? Yeah, so no. I guess what I'm planning next week is kind of just to kind of go through the past PowerPoints, talk about some concepts, review some concepts. So I guess after we do the review, there'll be the review videos, I guess, that I'll post on YouTube. Okay, and I'm not planning to post a practice final exam because the questions will come really from your midterms, and so you've got access to all of your midterm exams, and so you can just I think really the best way to study is really go through those exams, and I'll see if I can maybe open them up so you could take them again, kind of not for credit per se, but I'll try posting them on Blackboard so that you can take them for, so that if you're getting them right or wrong or something like that. So I'll see if I can do that, and I will let you know just as a review. So, all right. Hey, well, have a good day, everybody. See you on Wednesday.